if you want to prove that the period of a spring is equal to this, you first have to ask what is a period, and you should already know that at this point. A period is the amount of time it takes to go from one of the extremes back to that extreme. So it's the amount of time that passes in this interval.
So 5 points.
So what we're going to do is we're going to cut it in half and see how much time it takes from one extreme to the other extreme, and then double that. So in fact, we're actually going to cut that in quarters. We're going to see how much time it takes to go from one extreme to the equilibrium, and then multiply that by 4.
Can you also draw the spring? So
that is exactly what we're going to do. Please give me 1 second. We have a spring here at equilibrium. This is the spring when it's at one of its extremes. So when it's at equilibrium, it's moving at its fastest. So this is the kinetic energy, and the potential energy is equal to 0 because the displacement is equal to 0. And then when it's over here, well, why are we using the conservation of energy approach? That's probably not the best approach. You know what is the best approach?
Well,
just finding it using the Lagrangian.
No, use the mechanical energies because.
Okay, fine. No, but that's not going to find you the time.
Oh yeah, time is period. Period is 2 pi.
Yeah, you're not going to be able to get the time from that. So give it 1 second. All you have to do is use Newtonian mechanics, not Lagrangian mechanics, and realize that the forces acting on this are, well, there's only one force, the restoring force. So that means that m multiplied by a, which is the double derivative of x with respect to time,
can you just write F equal ma?
Is equal to the total force. And the total force is minus k multiplied by, well, x. Right?
Okay, that's fine. But instead of that, can you write F equal ma?
Yeah.
There is no need to be fancy.
What do you mean? This is the definition of acceleration. And there is a need to do this, by the way. This is how you solve an equation. So you have minus k over m. X is equal to d squared x dt squared. So how do you solve this equation? Since this is proportional to this with a constant in between, you assume x is equal to e to the ct, where c is just a constant. That's what c stands for. Now, when you take the first derivative, this is going to be ce to the ct. When you take the second derivative, it's going to be c squared e to the ct. You cancel these out from both sides. C squared is minus k over m. C is the square root of, well, technically that's not how it works, but that is how it works. Sorry. This is the square root of k over m with an I added in between. So what does that mean? Well, our solution is the real part of e to the I root k over m t. And that's just equal to alpha, or the amplitude, a, multiplied by cosine of the square root of k over m times t. So this is our function of position. Now, how do we find the period? Well, the period is how long it takes between two of the maxima of this function. How do we find the maxima? Well, the maxima is just what happens when we take the derivative of this and set it to 0. So you get minus a root k over m sine of root k over mt is equal to 0. Now see, this can never be equal to 0. Unless, of course, the spring is at rest. Which means that this is the only part that matters. So how far apart are the solutions to this equation? Well, sine of x's normal period is 2 pi. But when you multiply its frequency by the square root of k over m, the period is going to be 2 pi multiplied by 1 over the square root of k over m, which is 2 pi times the square root of m over k. You know, if you increase the frequency, you decrease the time it takes to go back to the original position, so you're decreasing the period. So that's what this gives us.